Chapter 6 for Stat 210, we start talking about the normal distribution. So the normal distribution is one of our continuous distributions that we are going to talk about really for a lot of this semester. So last chapter we talked about continuous random variables in general and continuous distributions in general, and then we talked about the uniform continuous distribution, and that kind of got us a little bit prepared for talking about the normal distribution. So the normal distribution we're going to see for most of the rest of the semester. Let's just dive in and start discovering a little bit more about it. So in this chapter, we will learn how to recognize normal probability distributions and how to apply them appropriately. We will learn how to recognize the standard normal probability distribution and its connection to the normal distribution. And this chapter really just introduces us to the normal distribution, which is probably one of the most important of all the distributions that I'm going to teach you this semester. And the distribution of many continuous random variables fit or approximately fit to the normal distribution when certain things are applied to them. So we're going to kind of dive into what is the normal distribution this chapter, and then we're going to kind of build on that over the next few chapters. So the normal distribution, there are two parameters for the normal distribution, the mean and the standard deviation. So here we have a nice pretty bell curve. The bell curve is what we look at for the normal distribution. There's a few other distributions that have this sort of shape to it, but the normal distribution is probably the most prevalent of all of those. So the blue curve of the normal distribution is given by the function f of x, where f of x is this wonderful equation here. Now, for most of you, you're like, oh my goodness, this is crazy. I don't want to see this formula ever. I don't want to have to use it. Well, don't worry, you don't have to use it. So as we kind of talked about in chapter 5, the normal distribution is one of those distributions where we can't find the probability underneath the curve unless we know calculus. So if you know calculus, you could take and integrate this between 2 points, and you'd be able to find the area underneath the curve, but above the x-axis. But without calculus, we can't do this without the help of a nice function on our calculator or some sort of table that we're given. So the normal distribution. So a few things to keep in mind about the normal distribution as we're moving forward is there's an endless number of normal distributions, and that's because each distribution depends on the mean and the standard deviation. So anytime that I change the mean, I've got a whole new normal distribution. Anytime that I change the standard deviation, I have a whole new normal distribution. So you're always going to be given the mean and the standard deviation for each of your normal distributions. Now, the formula is messy. We have no nice way of calculating the area underneath the curve without calculus. So we're going to have a few tools that are going to make things kind of easier. And as we look at this, we're going to kind of take a little bit of a road trip, per se, through history. And we're going to start with the empirical rule. The empirical rule was kind of your first tool that was used by mathematicians to figure out probabilities within the normal distribution. From there, some distribution tables were created, which made life even easier. We were able to be more precise. And then kind of flashing forward to modern day, we have calculators that have the ability to calculate normal probabilities for us. So let's start with the empirical rule. If a distribution is normal, then the empirical rule says that about 68% of the data values will fall between -1 standard deviation and +1 standard deviation of the mean mu. It also says that about 95% of the x values lie between -2 standard deviations and +2 standard deviations of the mean. And about 99.7% of the data values will lie between -3 standard deviations and +3 standard deviations of the mean. So this is kind of a picture that kind of helps us see things. So if our mean is here in the middle, then between these red lines that I'm drawing, we have 68% of the data. Between the blue lines that I've drawn, we have 95% of the data. And between the black lines that I'm drawing, we have 99.7% of the data. Now, the normal distribution is symmetrical about our mean mu. So if we have 68% is between the red lines and this purple line is exactly in the middle of them, that would mean that there'd be 34% in each of those little areas. Now, if we know that 95% is between the blue lines, but 68% was between the red lines, then we would have 95 minus 68 is 27. We have 27% to split between those areas there. So divide that by 2. That would mean that each of these areas would have 13.5% of the data. And then looking even further out, 99.7 minus 95 and divide it by 2. There's about 2.35% of the data in there and 2.35% of the data there. Now on the outside, we have 0.03%. Divide that by 2. That means out here there's 0.015% of the data, and here there's 0.015% of the data. Now, what does this mean for us? Well, if you're given your mean mu and your standard deviation sigma, then we should be able to use this empirical rule to at least guess at the probabilities. And in fact, if you're given a value that is exactly -1 and +1 standard deviations away, you'd be able to say, oh, hey, the probability between that is exactly 68%. So we're going to kind of use this a little bit to kind of help get our feet wet with the normal distribution. And then we'll move on to learning a little bit more about the normal distribution. So empirical rule. Let's use it. So an example using the empirical rule. The mean length of a particular breed of snake is 170 centimeters. So this is our value for mu, with a standard deviation of 6.28 centimeters. So that is my value for sigma. If snake lengths are known to follow normal distribution, let x equal the length of the snake. What is the percentage of snakes of this breed that are between 157.44 centimeters and 182.56 centimeters? So thinking how many standard deviations away, we're really thinking, what is my z-score for each of these values? Okay, so for 157.44, the z-score is -2. For 182.56, the z-score is +2. Now, thinking about our empirical rule, we know the probability of being between -2 and +2 standard deviations from the mean. That is 95%. So the empirical rule states that 95% of the data will fall between -2 and +2 standard deviations from the mean. So that means 95% of snakes of this breed are between these two values. Another example here. The scores in college entrance exams have an approximate normal distribution with a mean, so mu, of 52 points, with a standard deviation, so sigma right here, of 11 points. About 99.7% of the scores are between what two scores? 99.7. That goes with the -3, +3 standard deviations. So we're saying, what values have the z-scores of -3 and +3? So we're saying, okay, with our z-score formula, your z is equal to your data value minus the mean divided by sigma. We're saying we know a few things. We don't know the data value. So we're kind of solving for x here. So we would take, find a nice spot to write here. So it's like we're saying, okay, we're going to use this right here, and I'm going to solve it for x. So we're going to multiply both sides by sigma. So we have z times sigma equals x minus mu. So that means mu plus z times sigma equals x. So we plug in mu we plug in Z, we plug in sigma, we get X. So that means one of our values is 19. So we plugged in -3 first, then we plug in +3, get our other value. So we're saying that 99.7% of the scores fall between 19 and 85. Now, the empirical rule really has a lot of limitations to it. It only works if we're looking at values that lie 1, 2, or 3 standard deviations above or below the mean, which is super limiting. Another thing is most of the time we're not looking at values that are just these values, so we might need other tools. Other tools means a little bit more work, but more precision. So the next tool that we will look at is distribution tables. And distribution tables really can do everything that the calculators can do. Maybe they're not quite as fun to use because calculators are a little bit more fun, but the distribution tables really can do everything that you will need. So distribution tables were created by mathematicians to for people to reference and to help them find probabilities within the normal distribution. And really there's other distributions that we'll see some distribution tables for as well. These tables are handy, but remember there's an endless number of normal distributions. So that means we would have to have an endless number of tables. We need a solution to that. So our solution is let's just standardize the normal distribution. And this creates the standard normal distribution. So let's take a little bit of a side trip, talk about the standard normal distribution, then we'll come back to talking about distribution tables. So the standard normal distribution. We can easily standardize the normal distribution by using z-scores. We know z-scores, we're used to z-scores, and z-scores tell us how many standard deviations away from the mean that a value is. Okay, so the standard normal distribution will have a mean of 0 and a standard deviation of 1. Now, z-scores will be found using the same method that we've used previously, which we've used that sum today. So z equals x minus mu divided by sigma. Okay, so if we have the z-score, something in standard normal distribution, then we will be able to use the distribution table because there's just going to be one distribution table and it's going to be for the standard normal distribution. It makes life easier. You'll need like one page, maybe front and back for your distribution table. All right. Now the distribution table is always going to give you a probability where you're looking at the probability z is less than little z. So whenever we see a z, we're going to know that we're in standard normal distribution. Z means standard normal distribution. Make a note of that somewhere because you'll want to remember that when you get to your homework. And standard normal distribution means the mean is 0, the standard deviation is 1. So if we were given something like the probability that z is greater than little z, we would have to use our complement rule to rewrite that. So we'd be doing 1 minus probability that z is less than little z. It gives us the same thing. We're using the complement rule. Now, if you're looking for the probability that you're between two different values, what you're going to do is you're going to take the probability that z is less than the larger value and you'll subtract off the probability that z is less than the smaller value. So what your table is doing is it's giving you the area really to the left of some line, and say that we had some A and B here. We wanted to find the area between them. So probability that z is less than b is going to give us all of that area there in red. That is probability z is less than b. But I just wanted the area between the two black lines. Well, probability z is less than a is that blue area. So if we take that away from the red area, then I just have the area between the two lines. So this slide might be pretty handy to keep close by when you're working on your homework, because if you're using your distribution tables, this is going to be useful for making sure that you're using the correct values from your table to find your probabilities. All right. So let's go ahead and grab a distribution table, and we're going to find the probability that z is less than negative 1.19. Now, distribution tables should be available to you on Blackboard. You could also do a Google search and find them if you didn't want to use the same one that I have posted on Blackboard. That's fine. Distribution tables that you find will be accurate to somewhere between 3 and 4 decimal places. The one that I have here, for the most part, is accurate to 4 decimal places. There's a few of them that it has a few more decimal places given. There's going to be 2 different pages to your distribution table. There'll be one that'll have negative z-scores, and there'll be one that'll have positive z-scores. Now, negative z-scores are going to be for values that are below the mean, and positive z-scores will be values above the mean. So if we were looking for the probability that z is less than negative 1.19, what we're going to do is we're going to come down here, and we are going to find negative 1.1. So we'll be right there. And then the last digit here, this 9, is going to come from this other column over yonder. That'll be coming over here. So before the decimal place and the first decimal place digit will come from this first column here along the left, and then your second decimal place for your z-score is going to come from across the top. So where those intersect gives us a probability. So the probability that z is less than negative 1.19 should be equal to 0.1170. Now we're going to practice finding a couple more, making sure that we know how to use this table. And again, we have z, so we know we're in the standard normal distribution. And the standard normal distribution is what your table talks about, and it's where the mean is 0 and your standard deviation is 1. So let's find another one. Let's find the probability that z is greater than negative 2.43. Now, greater than, we're not able to use the table directly when we have greater than. We have to rewrite it. Okay, so rewriting it, we use the complement rule. 1 minus probability that z is less than negative 2.43. Now we're in a continuous distribution. So continuous distribution, that equals doesn't really matter to us because being equal to something, the probability is 0. We talked about that in chapter 5. So we would be able to say that this is the complement rule here. So we're going to do 1 minus whatever probability we find for this right here. All right, so we're going to find negative 2.4 along the left and then 0.03 along the top. And we see that those intersect at 0.0075. So we do 1 minus that, giving us 0.9925. Okay, the table's really not that bad. Let's try another one here. Let's find the probability that z is less than some value c is equal to 0.3632. You're like, wait, what? Aren't you supposed to give me the value right here and then I find this other value? This is like working backwards. How do we work backwards? Okay, working backwards. What we're going to do is we're going to find the value in the table that is as close as possible to this 0.3632. Now, we may not be able to find exactly that value. We're going to find the one that is the closest to it. So looking around in our table, the closest one that we see is down there. So we're looking all the way down here. We find this one. Hey, it's exactly it. So that's coming from negative 0.3 and 0.05. So negative 0.35. Let's go ahead and try another example. What if I said probability that z is greater than c is equal to 0.8245? You're like, whoa, okay, we have a greater than there. Our table doesn't give us greater than, so we'd say 1 minus, right? So that would be the same as saying that probability, instead of probability being greater than, the probability being less than is equal to 1 minus that probability. So we're saying 1 minus 0.8245 is the probability being less than. And then I've simplified it right there for you. So now we've got to get the closest thing to 0.1755. So looking for 0.1755. Now, we can't find exactly that, but we found something really close, right? We were able to find 0.1762. That's the closest thing we were able to see. So it's coming from negative 0.93. So we'd say this is approximately negative 0.93. Has an area to the right of 0.8245, which means an area to the left of 0.1755. So that kind of gets us started with using the distribution table. Here, we've only been looking at things that have negative z-values. We'll see things with positive z-values as we continue on this chapter, but I wanted to just kind of stick with using the same distribution table page as we worked through so far. Now, if you don't have the standard normal distribution, you can still use a distribution table. You just first have to standardize. So to standardize, you're going to change your x's into z's. Because remember, z's is when we have the standard normal distribution, where the mean is 0, the standard deviation is 1. So we're going to do this by using z-scores. So you're going to change your values into their z-score. Okay. Once we have our values changed into their z-score, we can use the table. So let's go ahead and try some examples here. The final exam scores in a statistics class were normally distributed with a mean of 63, a standard deviation of 5. Find the probability of scoring more than a 70 on the final. Okay, so we have a mean, which means we have mu. We have a standard deviation, which means we have sigma. We're looking for more than 70, so probability x is greater than 70. So change that to z-scores. For the probability z is greater than 70 minus 63 divided by 5. So the probability z is greater than 7 over 5. Change that to decimals because we'll need it for in decimals for our table. The probability z is greater than 1.4. Now, in order to use our table, we're going to have to use our complement rule because we need a less than symbol, not a greater than symbol. So probability z is greater than 1.4 is equal to 1 minus the probability that z is less than 1.4. So we're going to pull up a distribution table and we're going to find the probability here. So we're going to find this using a distribution table on the next slide. So here's a distribution table that has all the positive z-scores. We are looking for 1 minus the probability z is less than 1.4. So 1.4, the next decimal place would be 0. So we're working in that first column of probabilities there. So there it is, 0.9192. And we're going to want to do 1 minus that value. So 1 minus that value gives us 0.0808. So probability of scoring more than a 70 on the exam then would be 0.0808. So we're able to start with the standard normal distribution and use our table, and we're able to start with any normal distribution, standardize, and then use our table. Now we can also do that working backwards thing, like the last two examples that we did when we were working with our negative distribution table when we first started using the distribution table there. So final exam scores, statistics class, normally distributed, mean of 63, standard deviation of 5. So again, giving us the mean, that was a bad job circling, the mean and the standard deviation. And it says, find the score that would put a student in the bottom 15% of the class. So we're wanting the probability of being less than whatever value is equal to 0.15. So basically 15% is to the left or below this score. Now we need to standardize. So probability Z is less than X minus 63 divided by 5 is equal to 0.15. So we always have to standardize before we use our table. Now, we're ready to go ahead and grab a table now. So we have our table. I already grabbed the negative table because I know that I'm below the mean. I know that I'm below the mean because I'm saying the area to the left of this is only 0.15. The area to the left of the mean is 0.5. So that means this value has to be to the left of the mean for sure. So we're looking for the probability Z is less than some value where that value is X minus 63 divided by 5 is equal to 0.15. So on the inside of our table, in here where all of these probabilities are listed, we are looking in here and we are trying to find the closest thing to 0.15. There it is, 0.1492. Just a little bit closer to 0.15 than the 0.1515 is. Okay, so what does it come from? It comes from a Z value of negative 1.04. So we're saying that this value in here then, this X minus 63 divided by 5 is approximately negative 1.04. So we'd set those equal to each other and we'd solve for X, giving us that X is equal to 57.8. So that means a score of 57.8% would put, or below that, would put a student in the bottom 15% of the class. Now, we've kind of seen some issues at the distribution table, haven't we? As we've worked through this, we've said, well, in order to use the distribution table, we have to first standardize. So it takes time. We could have a math error in there as we're doing that, right? So there's a little bit of room for error there. And then these tables only give our Z values between -3 and +3 and only accurate to 2 decimal places. What if I had a Z score that was accurate to 4 decimal places and I wanted to find that probability? Well, I'd have to round it to 2 decimal places and then find the probability, which means I'm not going to be near as accurate as I was wanting to be. Now, another thing is the probabilities are given accurate to 3 or 4 decimal places. Well, what if I wanted an accuracy of 6 decimal places? Not going to happen with this table. And another thing that we see is there's gaps between these probabilities. We saw that when we were trying to work backwards, saying probability X is less than C is equal to a number, that probability. And we were looking for the closest thing to that probability. And we saw that not all the time are we going to find that. We're just going to pick the closest one, which means that we're creating a rounding error there. So when a higher degree of accuracy is needed, we have to turn to another method. And that other method is going to be the calculator. And we're going to go through and kind of redo these problems that we've done using the calculator, and we'll compare them and think about what did we get when we did this by hand? Did we get the same answer or not? And what we're going to notice is that we actually get approximately the same answer. When we're rounding it either 3 or 4 decimal places, we're getting the same answer, which really kind of frees it up for you guys to choose, I want to use the calculator or I want to use a table and do this by hand. So calculators can be very useful. Underneath the distribution menu, which you've accessed before, you'll find the normal CDF and the inverse norm functions. So this is where we're going to the distribution menu, so second vars. And this is where we found our binom CDF, binom PDF, Poisson CDF, Poisson PDF, those functions, same menu. And you're going to find that the normal CDF and the inverse norm, which is what you're going to use here, are towards the top of this menu. So with the normal CDF, you're going to enter your lower bound, then the upper bound, then the mean, and then the standard deviation. I'm going to give some examples of this in just a second. And then with the inverse norm, you're wanting to enter the area to the left, the mean, and the standard deviation. So if you're looking for the probability that x is less than some value, you'd be doing normal CDF, negative infinity, x, and then your mean and standard deviation. So what you're doing is you're thinking, looking at x is less than x, you're kind of turning that into your interval notation, which if you've taken a college algebra class, you've probably used interval notation, and that's kind of becoming those first values right there. And we see that again with the next one. We're saying x greater than x, using that to find your lower bound and your upper bound. Your mean and your standard deviation are being given to you. If you're in the standard normal distribution, your mean is 0, your standard deviation is 1. So if you have a z means you're in the standard normal distribution, so mean of 0, standard deviation of 1. If you're looking for the probability of being between two values, again, you're saying, okay, using interval notation, change that to interval notation. That gives me my lower and my upper bound. Now, if you're given C and you're looking for X, you would use inverse norm. C is your area to the left, the mean, and then the standard deviation. If you're given this, C is going to be equal to the area to the right. So the area to the left then is 1 minus C. So inverse norm, area to the left is 1 minus C, and then your mean and your standard deviation. Now, the biggest problem that you're going to find here using these formulas is that you can't type infinity or negative infinity into your calculator. Thankfully, your calculators will recognize 10 to the 99th power as being approximately infinity, and it recognizes negative 10 to the 99th as approximately negative infinity. Do make sure that when you're typing the negative 10 to the 99 that you use the negative symbol and not the minus sign. The minus sign, it'll throw an error. Make sure that you use the negative symbol. The negative symbol, I believe, is located right below the 3 on your calculator. So make sure you're not using minus, but you're instead using the negative symbol. There is a difference in those on your calculator. All right, so let's rework some of our problems. So reworking some of our problems. Now I have all of the answers showing here so that you can work through them at your own speed. I'm going to kind of talk about it as you work through them here, because I don't think there's a huge point in me just going through and saying, type this, type this, type this, type this. You're intelligent human beings. You can type things in yourself. So what we have here is we're saying using the normal CDF function. This is going through those first 4 examples that we did when we first used the table. Same exact examples, and what you're going to notice is we find the same answers. So the first one, we're using the normal CDF. We have a lower bound of negative infinity, upper bound of negative 1.19, and we know that our mean is 0 and our standard deviation is 1 because we have z, and we're finding that the probability is equal to 0.1170 when rounding to 4 decimal places, and that's exactly what our table gave us as well. With the next one, we have z is greater than negative 2.43. Now, when we were using the table, we had to use the complement rule to rewrite this. With our calculator, we don't have to. We're able to just say, okay, what's my lower bound, what's my upper bound, and then mean and standard deviation, and it gives us our answer. And what we see here is we still get the same answer that we got from our table. So we get the answer of 0.9925. Same answers we got from our table. The next two, kind of working backwards here, starting in the standard normal distribution with a mean of 0, standard deviation of 1. When we were looking for the probability that z is less than c is equal to 0.3632, this was the one that we were able to find exactly on our table. You're not always going to be able to find it exactly, but here we found it exactly on our table. And we found on the table that it was negative 0.35, and that's exactly what we find from the calculator as well. The next one, we weren't able to find exactly on the table, and we had to go through and use our our complement rule as we went through and did it as well. And here we do have to take into consideration that we have the greater than symbol. Whenever we have the greater than symbol and we're working backwards, we're using 1 minus the area that we're given. So we're always saying what's the area to the left. And this is one thing that I like to do, is I like to draw pictures. So on either of these last two, I would typically draw a picture where I have just kind of this basic curve. My mean is 0, my standard deviation is 1. And I'll just kind of like label things here for myself. That's my mean. And I'm saying, okay, I'm wanting to find something that has an area for this last one here. It's pointing to the right. So to the right, that is 0.8245. So I know it's going to be over here to have 0.8245 to the right of it, because to the right of the mean is 0.5, to the left of the mean is 0.5. Okay, so I have this picture drawn. I'm looking for this value C here. And I'm saying, okay, well, what's the area to the left then? The area to the left is 1 minus 0.845. So in your calculator, you can actually type in 1 minus 0.8245 if you wanted to, or you could simplify that and then type it in your calculator. Either way, still works. But your calculator is going to give you approximately negative 0.93. And that's actually what our table gave us, was negative 0.93. Now, if you're wanting a higher degree of accuracy, yes, your calculator gives you more than just 2 decimal places here. So you could have a higher degree of accuracy, but if you're just rounding to 2 decimal places, you're going to be getting the same answer. Now, going back through our other 2 examples using the calculator instead, final exam score in a statistics class normally distributed with a mean of 63, standard deviation of 5. Find the probability of scoring more than a 70 on the final. So you're doing normal CDF. Your lower bound is 70, upper bound is infinity, so 10 to the 99. Your mean is 63, your standard deviation is 5. You're getting exactly equal to 0.08075671112. When you round to 4 decimal places, you get exactly what we got before. And then finding the score that would put a student in the bottom 15% of the class. Saying the probability that x is less than little x is equal to 0.15. So it means x is equal to inverse norm, 0.15, which is your area to the left. We know it's area to the left because our inequality symbol is pointing to the left. So inverse norm, 0.15, 63, then 5, gives us 57.81783331, which is approximately 57.8, exactly what we got before. So what we're seeing here is our calculator can give us more accuracy, but when rounding to the same number of decimal places you would get from the table, it's giving you the same answer, which is nice. That means you can choose either one as you're working through this on your homework or on a test. Now, calculators have limits too. So calculators are only as useful as you make them. So be careful when you're doing things with your calculator. By relying solely on your calculator, you're not necessarily thinking critically about the problem, and it's going to be pretty easy to have errors that come up by just simply entering something wrong on your calculator. So be careful when you're entering things in your calculator. Make sure that you have some sort of guess as to what answer you should be getting before you go through and do the problem. And the empirical rule can help with this. Like, you know, your empirical rule helps give you an idea of what you might get for an answer. And then by using your calculator, then you'll be able to say, oh, hey, yeah, I got something close to what I thought I would get based on the empirical rules. I must have done things correctly. Or if you get something completely far off from that by using your calculator, you'd be able to say, hey, let's look back at and maybe see where my error came from. So make sure that you're still thinking about your problem, even if you're using your calculator. Now, it's best to make sure that you have a grasp on what your answer should be so you catch those calculator errors. But as long as you have a grasp on what you're doing, or general grasp on what you're doing, the calculator is going to save you time in the long run. Just make sure that you are taking your time with it.